Have you ever stopped to think about how your computer actually talks to a server to load a website? Or how you can play an online game with people all over the world in real time? Well, the answer to pretty much all of it is something called socket programming. It's the absolute bedrock of internet communication, and in this explainer, we are going to break down exactly how it all works, from the ground up.
So here's our game plan. We're going to start with the absolute basics, what a socket even is. Then, we'll get into the client-server model, which is kind of the rule book for these conversations. After that, we'll dive into the two heavyweights of the internet, TCP and UDP, and figure out when you'd use one over the other. We'll even touch on some advanced stuff before we wrap up by showing you how you're using all this tech every single day.
All right, let's jump right in. Before any data can go anywhere, an application needs a doorway to the network. And that doorway, well, that's a socket.
So really, what is a socket? Think of it like a digital plug or an endpoint that an app on your computer uses to connect to the network. It is the crucial link between your program, your web browser, your game, whatever, and the underlying network protocols like TCP or UDP that are actually doing the heavy lifting of sending the data. Without a socket, your app is just an island, totally isolated on your machine with no way to talk to the outside world.
Okay, so how does the network know exactly where to send stuff? I mean, a socket isn't just a generic plug. It has a totally unique address, and that address is made of two key parts. First, you've got the IP address. That's like the street address for a specific computer on the internet. It answers the question, who are you? But a single computer can be having tons of different conversations at once. That's where the port number comes in. Think of the port as the specific apartment number at that street address. This is why you always see those standard numbers like port 80 for web traffic or 443 for secure sites. Each port is a different door for a different conversation. And together, that IP and port number create a one-of-a-kind address, making sure your web request doesn't accidentally end up in your email inbox.
So we know what a socket is, but how do these conversations actually play out? Well, they follow a really clear pattern called the client-server model. This is, hands down, the fundamental architecture for pretty much everything we do online.
Let's look at the server's job first. A server really is just waiting for someone to talk to it. Its whole workflow is kind of passive, but always prepared. First, it opens a socket. That's its door to the network. Then it binds that socket to a specific port number, basically claiming, hey, I'm handling all the web traffic at apartment 80. After that, it just listens. It's patiently waiting for a client to come knocking on that specific door. When a client finally connects, the server accepts, and only then can the real communication actually begin.
The client, on the other hand, is the one making the first move. It's the active participant that starts the whole conversation. So first, the client creates its own socket, but instead of listening, it actively tries to connect to the server using that server's known IP address and port number. Once the server accepts that connection, they can start sending data back and forth. And when the conversation's over, the client usually just closes the connection. This fundamental dance between client and server is happening millions of times a second all over the planet.
And now we get to the really cool part. How does the data actually get from point A to point B? The first method we're going to look at is TCP, which stands for Transmission Control Protocol. And you need to remember this. When you absolutely positively need your data to arrive in one piece, you use TCP.
There are three words that you have to associate with TCP: reliable, ordered, and connection-oriented. Reliable means TCP guarantees that what you send is what gets received. It checks for errors and will resend any lost bits. Ordered means if you send packets in ABC order, TCP makes sure they get put back together in ABC order on the other side. And connection-oriented means that before a single byte of data is sent, a formal connection has to be established between the client and the server. So, how does TCP build that super stable connection? It uses something called the three-way handshake. It goes like this. First, the client sends a SYN packet to the server, which is basically it's saying, hey, can we sync up and start talking? Then the server, if it's available, replies with a SYN-ACK packet, which means, yep, I got your request and I'm ready to talk too. Finally, the client sends back one last ACK or acknowledge packet, saying, awesome, I see you're ready. Only after that three-step confirmation is the connection officially open and ready for data.
So where do we see this in the real world? Well, think about anything where getting the data right is non-negotiable. When you're loading a web page, you need every single piece of that page to show up correctly, right? When you're sending an email, you definitely can't afford to have words missing.
File transfers, database queries, secure logins, all of these absolutely depend on the guaranteed delivery that only TCP can provide. But what if guaranteed delivery isn't your top priority? What if what you really care about is just pure speed? Well, for that, my friend, we enter the fast lane with UDP, the User Datagram Protocol.
UDP is the total opposite of TCP. It basically throws all that careful setup and verification right out the window. There's no three-way handshake. There is no formal connection. UDP just grabs your data, shoves it in a packet called a datagram, and just flings it toward the destination. It doesn't wait for anyone to say, "I got it." It just sends and hopes for the best. And the trade-off for that unreliability? Incredible speed.
So here's the bottom line with UDP. There are absolutely zero guarantees. A packet might get lost on the way, and it's gone forever. It's not getting resent. Packets might show up out of order, and UDP is not going to bother rearranging them for you. But because it doesn't have to manage any of that complexity, its data packets have way less overhead than TCP's. This is what makes it a super lightweight, fire-and-forget kind of protocol. So you might be thinking, when would you ever want to use something so reckless? Well, anytime speed is more important than perfect accuracy. In a fast-paced online game, you'd much rather miss a single frame of data than have the entire game freeze to re-download a lost packet. Same thing for a video call. A tiny glitch for a split second is way better than a long delay. Live streaming, quick DNS lookups, tiny sensor data updates, all of these things need low-latency communication, which makes them perfect for UDP.
This table really puts it all side by side, and the contrast is crystal clear. On one hand, you have TCP, with its handshake, its guaranteed delivery, and slower speed, which is perfect for web and email. And on the other, you have UDP's connectionless, no guarantees approach that gives you the raw speed you need for gaming and streaming. It's never about which one is better, it's always about picking the right tool for the job.
Okay, now for anyone building really high-performance applications, there's another layer to think about: how the socket itself behaves when it's waiting for data. And this brings us to a concept called blocking versus non-blocking sockets.
By default, sockets are blocking. So what does that mean? It means when your program asks to receive data, your entire application just freezes and waits until that data finally shows up. This is simple to code, but just imagine a server trying to handle thousands of clients. It can't just grind to a halt waiting for one person. And that's where non-blocking mode comes in. In this mode, if the data isn't ready, the call just returns immediately, which frees up the server to go handle other clients. It can then just circle back and check again later. This efficiency is the secret sauce behind modern, high-performance servers that can handle a massive amount of traffic.
We've covered a lot of technical stuff, I know, but the amazing part is that you interact with these concepts every single minute that you're online. Let's bring this all back to your daily life. Every single time you type a web address into your browser and hit enter, that browser is opening a TCP socket to a web server to download the page. The rock-solid reliability of TCP is what makes sure all the images, text, and code arrive perfectly. When you send an email, TCP ensures your message gets there without any words getting mixed up or lost. Logging into a remote server, pulling data from a database, all TCP, all the time, because in those cases, accuracy is everything.
Now on the flip side, every time you jump into a multiplayer game, your device is just firing off a rapid stream of UDP packets with your position and actions. That low latency is what makes the game feel so responsive. When you're on a Zoom call, your voice and video are being sent over UDP to keep the conversation flowing smoothly, even if you get a tiny visual hiccup. Even something as basic as your computer looking up a website's IP address with DNS often uses UDP for a super quick query and response.
So, let's wrap it all up. Sockets are the doorways to the internet, and they communicate using two main rulebooks. You have TCP, the reliable tortoise, making absolutely sure every piece of data arrives safe and sound. And then you have UDP, the fast hare, prioritizing raw speed above everything else. From your web browser to your favorite online game, this fundamental duo powers almost everything you do.
And that brings us to a final thought. Imagine you're an engineer and you're building the next huge live streaming platform. For the core video stream itself, the part people are watching in real time, would you build it on the reliable foundation of TCP, or would you go with the raw speed of UDP? What are the trade-offs you'd be making with that choice? That's the exact kind of decision network programmers make every day, and now you understand exactly what's at stake.